Hi. Hi everybody. In this video, we'll talk about another important concept in linear algebra, that is bases. So we can extract a bit more from the intuitive idea that subspaces are generalizations of planes through the origin in R3. A plane is spanned by any two vectors that are parallel to the plane but are not parallel to each other. In algebraic parlance, two such vectors span the plane and are linearly independent. Fewer than two vectors will not work, and more than two vectors is not necessary. And this is the essence of a basis for a subspace. Actually, when I talk about basis, we should just understand that it is the principal component of something. Since we are talking about vector spaces, right? So these are the principal vectors. So they form that space. Okay, let's start with this definition. A basis for a subspace S of Rn is a set of vectors in S. And here we have two conditions, two properties. Number one, it must span S, and those vectors must be linearly independent. Span S means, okay, here we are talking about, okay, Rn, this our n-dimensional space, and a basis for a subspace S. So we are talking about a subspace. Here we have subspace, okay, and here we are talking about maybe here finite or infinitely many vectors in S, okay. So we are just talking about the basis vectors here. For if you're talking about a bunch of vectors, to form a basis for S, number one, it must span S. And that means that if you just pick any vector from S, we should be able to write as a linear combination of these vectors, basis vectors. And number two, these vectors must be linearly independent. If actually it holds these two properties, then we say that actually these vectors or set of vectors, they form, what is it, a basis for subspace S. Let's start with this example. Standard vectors E1, E2, En. In Rn, they are linearly independent and span Rn. Therefore, they form a basis for Rn, and we call them the standard basis. For example, here, immediately, we just consider in this case, how about if n equals 2? Then we are talking about two-dimensional space. So our unit vectors here, let's say the first one is this, 1, 0, and the second unit vector is, second standard unit vector is 0, 1. So now I have to show that actually it satisfies those two properties, right? It actually holds those two properties. Now, it's here it says that linearly independent. Actually, these two vectors are linearly independent because scalar multiple of 1, it doesn't actually produce the second vector. But if you just multiply, for example, E1 by any constant, it will be K0. It will never be equal to 0, 1 here. That means that these two vectors are linearly independent. Okay, that's the first property. And the second one is we have to show that it spans Rn. But in our case, it spans R2. It means it just fills all of their linear combinations. Actually, they fill this R2. Now, to show this one, I have to show that if you just pick any vector whose coordinates are, let's say, x and y, okay, from R2, I should show that I can find such numbers that C1 and C2, the linear combination gives us this. Actually, it's always I can write as a linear combination of these two vectors. How? This x and y, and here we have x, y, can just write it as x times 1, 0 plus y times 0, 1, right? And actually, that's just x times the first vector, y times second vector. If you're given any vector, we can just write it as a linear combination of these two vectors. So also that means that it spans R2. So that's why actually these two vectors, R1 and R2, let's say this is this E1 and E2, they form a basis. And at the same time, we call them actually standard basis for two-dimensional space, because actually we have a lot of different bases, but we know that the number of vectors, maybe soon we will prove it as a theorem, the number of vectors in a basis, they are equal. And how about in our second case, let's say n equals 3. Okay, if n equals 3, then R3 and our standard unit vectors here is our E1, whose components are 1, 0, 0, and the E2, here we have 0, 1, 0, and the E3, okay, here we have 0, 0, 1. And we know that these three vectors are linearly independent vectors. We know how to show this because they are already, if you just write them in the matrix, right, they're already in reduced to echelon form. And actually, all this, what is it? We have three pivots here. So these vectors are linearly independent. Now we have to show that also it spans Rn. So again, I can show that, can I just show that if you just pick any vector, let's say this V from R3, any vector means here we have whose components are, let's say, x, y, z. Can we just write it as a linear combination of these three vectors? Yes, in a similar way, I can just write it as x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. If you just pick any vector, I can write it as a linear combination of these three vectors. That means that also actually these vectors form a basis for three-dimensional space. In this example, show that the vectors u equals to 3 and v equals, components are -3 and 1, form a basis for R2. In the previous example, actually, the standard unit vectors, right? They form a basis, and here we are just going to show that actually they form another basis, okay? Because a subspace can have more than one basis. So that is another basis. But soon we are going to prove in a theorem that actually the number of vectors in a basis, they are equal. So to show that, again, I have to show that if you just pick any vector, now from here we know that scalar multiple of 2, 3 is not equal to -3 times 1. And also the first property, how can we show that? Can we actually to be dependent, right? Actually, if you just multiply u vector u by some constant, it should give us v. Is it the case? Can we find k? It's not possible because if you multiply u by k, here we have 2k and here we have 3k. On the right hand side, vector v whose components are -3 and 1. If you solve for k in the first, actually using the first components, k will be equal to -3 over 2. And using the second components, k will be equal to 1 over 3, right? Actually, at the same time, k cannot assume two different values. So such number does not exist. That means that this u and v are linearly independent. And how about the second case? Now we have to show that it spans this space, R2. So that means that if you just pick any vector whose components are, let's say, x and y, I had to show that can I just find some numbers so that I can just show them as, I can write it as a linear combination of these two vectors. C1, the first one is 2, 3 plus, and C2, and here we have -3, 1. So we have already showed that actually these vectors are linearly independent. Now also we have to show that actually these vectors span R2. Then we can say that it forms a basis for R2. A basis for R2 means using only these two vectors, actually we can produce any vector in R2. That's the meaning of basis. So from here, what we have here, you know that we need to form our augmented matrix. So that is C1 and C2. These are unknowns here. I'm looking for the C1 and C2. Is it possible to find the C1 and C2? So here we will have augmented matrix here, 2, 3, and -3, 1. And here we have x and 1. So if we just reduce this to reduced row echelon form, here we have, let's divide, multiply the first row by 1 over 2. So here we have 1, -3 over 2, and x over 2. The second one, multiply by 1 over 3, 1, 1 over 3, y over 3. Right? So if you multiply the first row by -1 and add it to the second row, and here we have 1 minus 3 over 2 x over 2. And here we have 0 minus 3 over 2. Okay. If you multiply by -1, it is 3 over 2. Plus, we should add it to 1 over 3. That's equal to 11 over 6. So here we have 11 over 6. And how about here? We should multiply by -1 and add here. So here we have y over 3 minus x over 2. Fine. Okay. So now I should just multiply this by something and add to the first row. And here we will have 0 to do this. Let me just multiply the second row by 6 over 11. And here we have 1 minus 3 over 2, x over 2. And here we have 0. And here we have 1, 6 over 11. And here we have y over 3 minus x over 2. Okay. So now if you multiply this by 3 over 2 and add it to the first row, so here we will have 1, 0, here we have 0, 1, and multiplies by 3 over 2. So here we have 3 over 2 times 11, 6. Actually, here we have 6 over 11, and the y over 3 minus x over 2. And just multiply by, okay, 3 over 2, and adding this, so this plus x over 2. How about here? Here we have 6 over 11, and the y over 3 minus x over 2. Okay, you can simplify this. So as you see here, that means that the C1, that thing, right, that thing is C1, and this one is C2. For every real value of x and y, right, if you just substitute any number for x and y, here I can evaluate this. And we don't have such zero division or something like that. So for every value of x and y, substitute here, evaluate this, it gives us one real number. The same thing here. That means that this system is consistent. It has one solution, unique solution. So that means that if you just give me any vector from two-dimensional space, I can write it as a linear combination of these two vectors. That means that these two vectors span R2, and they are at the same time linearly independent. That means that these vectors form a basis for two-dimensional space. Once again, actually, as you see here, this is another basis for R2. And however, we will prove shortly that the number of vectors in a basis for a given subspace will always be the same. Since we're talking about two-dimensional space, and if you're talking about some different bases, let's say maybe this is one basis and whose vectors are E1 and E2. Now we got another basis here, and whose actual components are, let's say, this U and V. We can find another basis here, but now we know that the number of vectors in each basis, actually they are equal, only two vectors. Only one vector, it will not be enough. More than two vectors, it will not be necessary. And that is the essence of a basis. Okay, so another example here, find a basis for S equals span U, V, W, where U equals this, V equals this, and W equals this. Again, we are talking about, what is it? Here we are talking about three-dimensional space, and here we are talking about a kind of subspace here that is S, right? And this subspace is spanned by these three vectors, right? And actually already, because here it is spanned by these vectors. So we don't have to show that it spans this subspace. We only have to show that here these vectors are linearly independent, right? Still, I'm not sure actually all of these vectors U, V, W to span this subspace. Do we have to keep all these vectors? If of course, we have to give all these vectors if they are linearly independent. If these vectors are linearly dependent, and we need to actually eliminate one of them. We don't have to keep all these vectors, right? Because after all, let's say these three vectors are linearly dependent. That means that at least one of these vectors can be expressed as a linear combination of the other vectors. Assume that one linear combination of u and v, it gives us w. So we don't have to keep this in our basis space, actually this subspace, because this vector I can produce this by using this u and v. Anyway, to show that, we will, to determine that if they are linearly dependent or independent, as you know, we have two ways. The first way is I can just write it as this u v w, and u is 2 3 1, and v is -1 0 5, and w is 5 9 and 8. So now, by applying a bunch of elementary row operations, if you reduce this to reduced row echelon form, what we got here? Here we have 2, right? And I should maybe multiply this by something, and at here we can have 0 here, multiply by 1 over 2, and subtract, or multiply by -1 over 2 and add it to the third row. Anyway, you know how to do that. Actually, by applying a bunch of elementary row operations, we can reduce this to this. So here we have 1 0 0, and 0 1 0, and here we have 3 1 0. That is the reduced row echelon form of this matrix. So now actually here the original matrix here, and it is reduced row echelon form. If we just denote this by, let's say, capital A, and this one is, let's say, R. And what is R? R is reduced row echelon form of A. Actually, between their columns, they have the same independence or dependence relationship. Because if we just apply a bunch of elementary row operations, right, we obtain reduced row echelon form of A. And by saying that, actually the columns have the same dependence relationship. As you see here, for example, as you see here, we have 0. That means that actually these are, what is it, linearly dependent vectors. So now that is our first row, that is the first vector. The second one, if I multiply the first column by 3 and the second column by 1, I get the third column, right? From here, if you multiply 3 times 1 0 0 and plus just the second column, and here we have 0 1 0, and now we get the third column here, 3 1 0. Actually, the same thing is true for this matrix. If you just multiply the first column by 3, 2 3 1, and plus the second column is -1 0 5, and that's equal to, here we have 3 times 2 6, 6 plus -1, it is 5, 3 times 3 9, plus 0, it is 9, 3 times 1 3, plus 8 5, that's equal to 8. Let's see here, it produces, what is it, the third column. Okay, now actually we are going to use this fact again soon. So that means that here we can just write this 3 times u plus v is equal to w. So this set is linearly dependent. So I don't have to keep this w here, right? So find a basis. What will be the basis then? Then the basis for this subspace will be only u and v. These two vectors are linearly independent, and these two vectors spans this subspace S. That means that if you just pick any vector that can be expressed as a linear combination of this u, v, w, I can also do that using only u, v. Okay, and because if you just write u, v, w, actually this set must be linearly independent to be a basis. Since it is not linearly dependent, now actually we just eliminated one of the vectors which is dependent on other vectors, that is w here. So if you just keep u and v, they form u and v forms a basis for the subspace S. Okay, another example is about a Lie matrix here. Find a basis for the row space of this. So when you just say again row space, we should just here understand that here how many rows does it have? It has 5 rows, right? Let's say this one is the first row and this one is second row, or it has 3 or 4 rows. Here we have B3 and this one is B4, right? And what is B1? B1 is this 1, -2, 0, 0, 3. And the B2, it is this vector 2, -5, -3, -2, and the 6. And the B3, it is 0, 5, 15, and 10, and 0. And the last row, it is 2, 6, 18, 2, 6, 18, and 8, 6. Okay. So now we are talking about, what is it? 5-dimensional space. And here inside this, and we are talking about the kind of set, right? That S, okay, that is spanned by these vectors, B1 and B2, B3, B4. Because when you just say row space of A, actually that is, what is it? Row space of A, right? So that is row space of A, and which is spanned by the rows of the matrix A. Okay, now since it spans this S, so this the first property holds, right? Now we have to show that these vectors are, what is it? These vectors are linearly independent. To show this again, we have to reduce this to a reduced row echelon form. If you do so, we will get that this matrix. So that is the reduced row echelon form of this one. Now from here, as you see here, actually applying a bunch of elementary row operations, right? It also produces a chain of, what is it? Linear dependence relationship. Now from here, if these vectors are linearly dependent, that means that we can produce 0 vector. And since here at the bottom we have 0 vector, that means that the last vector is just dependent on the other vectors. And if you remember that example from here, that means that we don't have to keep all these vectors here by just using the first 3 vectors, because here we have these pivots. Usually we just pick up the rows which has pivots. So this actually, these 3 rows have pivots, right? So I don't have to keep this the last row. Then the basis for, for the row space of this matrix will be these vectors. Let me just write here. The first vector is this one, that is 1, 0, 0, -2, 3. And the second vector is, what is it? 0, 1, 0, -1, 0. And the third one is 0, 0, 0, 0, 1, 0, 0. Okay, these 3 rows, actually, these 3 vectors, they form a basis for the row space of A. That means that if you just pick any vector from row space of S, that means that actually that vector is just obtained by linear combination of these 4 rows. I can express that vector as a linear combination of these 3 vectors. And these 3 vectors are linearly independent. Okay. So now the question comes, okay, instead of this, can I just directly take the first row and the second row and the third row? And also, of course, also actually the same thing. Also actually can just write these 3 vectors, because we know that these 3 vectors are linearly dependent, okay? And also these vectors actually living in here in subspace S and then the row space of A. Because as you know, the basis may be, the vectors in the basis, they may be different, but just, the condition to be basis, just they have to span this subspace, and after that, they have to be linearly independent. Okay, so now here we will consider a little bit different example here, but now we have to consider the column space of the matrix. So let's say here we are given matrix A, and it says that we need to find the column the basis for the column space of this matrix. And if you just write the columns of this matrix, how many columns does it have? It has 1, 2, 3, 4, 5. So actually I can just write it as something like this: A1, A2, A3, A4, and A5. So that is the first vector: A2, A3, A4, and A5. And each column has 4 components. Actually, these vectors, this AI, is taken from, what is it, 4-dimensional space. And here, of course, I change from 1 to 4, no, 1 to 5, sorry, 1 to 5. Again, to do this one, first we have to reduce the given matrix into reduced row echelon form. When you do so, you know how to do that by just applying a bunch of elementary row operations. I can reduce this A into this form, right? And also we know that the original matrix A, and it is reduced row echelon form, and they have the same dependence relationship between their columns. So that means that, as you see here, this column contains one pivot, and also this contains a pivot. This contains a pivot, but the third column, it does not contain, right? Fourth column, it does not contain. That means that the first 3 columns are linearly independent. So other columns are just dependent because I'm just using the first and second and third row. I mean, as a linear combination of this first and second and third column, I can produce this vector, or I can produce this vector. So I don't have to keep this in our basis, or I don't have to take them as a vector in our basis. So as see here, what does it mean? For example, if you multiply this 9, negative 4.25, 1.5, if you multiply the first column by 9, the second column by negative 4.25, and third column by 1.5, I will obtain the third column. Again, if you just check this, multiply the first column by 9, second column by negative 4.25, and third column by 1.5, we will obtain A4. And if you multiply the first column by 9.5, the second one by negative 2.5, and third one by 2, we will obtain the last column, A5. Okay. But of course, when you're just writing this, simply I cannot take these 3 vectors as basis vectors. Why? Because as see here, the last components are 0. And since we are talking about column space of A, right, our S is column space of A. It means that it's the set which is spanned by the columns of A, right? By just using these 3 vectors, their linear combination, I can never produce, for example, 2 here because they are always 0, right? But since they have the same dependence relationship, I should just take this A1, A2, A3 as our basis vectors. So the basis for the column space of A, it will be these vectors. The first column, that is 0, 0, 2, 2. And the second one is 2, 0, 2, 0, 2, 0. And the third one, it is 3, 2, 3, 2, minus 5, minus 6. So these 3 vectors, that is the first 3 columns of matrix A, they form a basis for the column space of A. Okay. All right. So now here we'll talk about the null space. And what is a null space? That is all the vectors, right, that takes to 0 vector. Okay, here we have another example. Find a basis for the null space of the matrix A. Here we are given matrix A and null space. So again, here there's really nothing new except the terminology. We simply have to find and describe the solutions of the homogeneous system. That is AX is equal to 0. Because null space means As you remember, we are talking about this, let's say this N, null space of A, all the solutions of this homogeneous system is here. Now here we should just describe the solution of the system. To do this one again, as you know, we need to write our augmented matrix. That is A, here we have A, and 0, right? And we have to reduce this to reduced row echelon form. And reduced row echelon form of A we have already done is equal to this, right? So now here we have reduced this thing into this form. Here we have R, and here we have 0, right? And if you just rewrite our system here, what do we have here? Here we have R and the times, and here we have X, not the product. On the right hand side, we have 0 vector. And because these two equations, AX equals 0 and RX equals 0, they are equivalent, right? And if we just write this X, it has 5 components, right? Because here we have 5 columns. And if you just write our system again, so the first one will be 1 times x1. Let me just change the color here. So here we have x1 and 0, 0. This one is 9x4 plus 9x4 plus 9.5 x5. That's equal to 0. And the second one, here we have x2 plus x3 0, x4, it is minus, so that is minus 4.25 x 1 2 3 4 minus 2.5 x5, that's equal to 0. And the last one, here we have x3 plus 1.5 x4 plus 2 times x5, that's equal to 0. As see here from this x1 and x2, x3, these are dependent variables, and x4 and x5, these are independent variables, right? So let's say here, let's say S equals x4 and T equals x5. Now what do we have here? Here then we will have x1 will be equal to minus 9, x4, that is S, minus 9.5, x5, that is T. And x2 will be 4.25 S plus 2.5 T. x3 will be minus 1.5 S minus 2 times T. And x4 is equal to S, x5 is equal to T. So now we can just write the solution, that is, here we have x1, x2, x3, x4, x5. That's the solution of the given homogeneous system. And first S, if I just keep it here, S, here we have the first one -9, and second one 4.25, third one minus 1.5, and here we have 1, here we have 0. Plus, and here we have T, and T minus 9.5, minus 9.5, and 2.5, 2.5, and here we have minus 2, and we don't have T here, it is 0, and here we have T, that is 1. Okay, that is like this. So let's say that is vector U, and this one is vector V. So the solution of the system, I can just write it as S times U plus T times V. And from here you can see that the scalar multiple of U is not equal to V. That means that these two vectors are linearly independent. And it spans the null space of A, right? Because you see here, any solution is just S times U plus T times V. So what is the question? The basis for the null space of the matrix A. So the basis for the null space of the given matrix will be, it is U and V, where U is this vector, and V is our second vector. Okay, now let's just conclude this, and we'll continue our class in the next video. So, the following is a summary of the most effective procedure to use to find the basis for the row space, the column space, and the null space of a matrix. Find the reduced row echelon form R of A, that's our first step, and use the non-zero row vectors of R containing the leading ones to find a basis for row space of A, and use the column vectors of A that correspond to the columns of R containing the leading ones, the pivot columns, to form a basis for column space of A. Solve for the leading variables of Rx equals 0, that's in our last example. In terms of free variables, set the free variables equal to parameters, that is x4 equals s, x5 equals t, what we did in the previous example. Substitute back into x and write the results, a linear combination of f vectors, where f is the number of free variables. These f vectors form a basis for null space of A. So in our the previous examples, example that U and V, actually they were the vectors in the basis of null space of A. Thank you.